Any object in the world that you could hit or shake or cause to vibrate is going to make a sound related to the mass of that object and its construction. For example, a ruler, a comb, a rubber band, you probably plucked these and heard them make a pitch or a sound. I have a particularly good example of such an object here. It's called a singing bowl and it comes from Nepal, and as I get it to vibrate, you can hear the richness of its sounds. These sounds are actually occurring in different pitches, each of which is a multiple of the fundamental pitch of the bowl. Let's see if we can hear the fundamental pitch of the bowl. Ah, do you hear that pitch right about there? Ah. Now you also hear other pitches. There's one a fifth above. Ah, do you hear that in the bowl? Ah. And also an octave higher. Ah. And even a third above that. Ah. I can't sing that well, but you can hear that. Now these pitches that we're hearing are all integer multiples of the fundamental pitch of this bowl. It makes a complex sound, but if you listen, your ear can pick apart the various different frequencies that are being reproduced. So most of the objects in the world, when they emit sound, are emitting a fundamental pitch, that is their fundamental frequency, as well as what are called overtones, or these integer multiples of the fundamental frequency. I'd like to demonstrate that on a guitar as well. On the guitar, I'm going to use the low E string here, and we hear its sound. Now the Sedgwick pitches that we're using in our work here start at 0, which is concert A, so here's the A pitch. And on the guitar, more so than on the piano, you can see that as I go up the fret, up the neck here, each of these is a chromatic step higher, a half step on the piano. So we go from A to A sharp, to B, to C. In terms of Sedgwick pitches, these are 0, 1, 2, and 3. Or we can go down from 0, from A, -1 to A flat, -2 to G, and so on. Now, if we wanted to see how the strings of the guitar relate to the singing bowl, one way to think of that is we have the string here, and how do we get a sound that's exactly an octave higher? It turns out on the guitar, the frequency of a pitch and the length of the string are actually reciprocals of each other. So if I could take this string and cut it in half, I don't recommend doing that. The guitar is not very playable after that, but suppose I could cut it in half, the pitch we would hear from that length of a string under the same tension would be an octave higher. Now on the guitar, instead of cutting the string, we can instead stop the string here, and the effective length of the vibrating string is the bottom part here toward the sound hole. So here's the fundamental pitch of the string, and here it is an octave higher halfway up the string. Those are actually an octave apart, and to many of us the pitches actually sound exactly the same. That's why an octave sounds so comfortable and familiar. So if that's half the length of the string, how do we get a fifth? Well, again, the length is inversely proportional to the frequency, and it turns out we'd like to create a length of string that is 2/3 the length of the original string. So if this is half, this is roughly 2/3, and that's the interval of a fifth from E to B. How do we get a fourth? Now we would like a length of string that's 2/3 the length of the original string, and that occurs right here. And that is a fourth above the E at an A. Now if a guitar could be pitched perfectly like the singing bowl is pitched, we could take the interval of a fifth from E to B, and the interval from the B to the next high E, which is a fourth, and those two would multiply together to give us exactly half, or a factor of 2 in frequency. But 4/5 times 2/3 is actually 8/15, which is not quite half. So the pure pitches that we hear from the singing bowl and all the objects in the world don't work out quite right on a fixed pitched instrument to get us the octave higher that we need to get, which is exactly halfway up the string. As a concession to that, the guitar and the piano and all pitched instruments place their notes a fixed distance apart in terms of pitch. It turns out the ratio of each half step, say from here to here, is exactly the 12th root of 2. That seems like a strange number, but if I take the 12th root of 2 and multiply it by itself 12 times as I go up the neck of this guitar, by the time I take 12 steps, the radical disappears, and I get an exact multiple of 2, and that gives us the octave we want. So 12th root of 2 from here to here, to here, to here, and so on, so that by the time I reach the octave, we get a factor of 2. Now we can take these pitches, and we will be combining them in our exercises and work in this course into chords. So I can take pitches starting at the E and create an E minor chord, or a C chord, or a G chord, or a D chord, and in one of the exercises we look at, those 4 chords form the basis of many of the songs we hear today.